And so in this particular example now, we got to think about our three equations. And Q is equal to MC times delta T. And that is the heat absorbed, right? And the heat produced, which we also call just Q slash heat, I think. The heat produced, if we're using calories, is equal to power times time divided by joules equivalent of heat, right? 4.187. And remember that the power and the time here got to be in base units, so watts and seconds, and that's very important. Now, these two formulas are related by the efficiency formula. And we know that the heat produced must be bigger than the heat actually absorbed because of the losses. Not all of it is absorbed. So this is bigger than Q. So that's what we got to keep in mind before we start. Okay. So we're given a bunch of information up here. You notice that you're given the efficiency. So you won't be asked to find that. So, you know, when you're asked to calculate the power consumed by the arc furnace, well, of course, the power is here. But the specific heat is important, right? Because the specific heat is in this equation. So that means start with heat produced, use your efficiency to find Q, and then solve this equation to find C. If you're asked specifically for something over here, which is usually time, you do that in reverse. You're given the information to find Q, use the efficiency to figure out the heat produced, and then figure out your quantity out of this equation, right? And so start here for this one, work your way over to C. So the first thing is the power consumed by the arc furnace. Well, P, got three formulas for P, right? And so let's think about the information that we're given. We're given the voltage and the current. So P then is equal to V times I. And we have 220 volts then multiplied by 10 amps. And that gives us 2200 watts. And so when we go ahead and calculate energy, we'll need that in kilowatts. And so I'll go ahead now and write 2.2 kilowatts here. So remember, divide by 1,000 converts to watts. Okay, for part B, the specific heat of the alloy. Again now, we'll start then by saying that the heat produced and that was supposed to be an R there. Is equal to power times time over 4.187. So the power in this one, base units, watts, 2200 watts. And we're going to multiply that by the time. And remember that the time here got to be seconds. And so that's very important because, you know, the formula has been defined with base units. 35 minutes means that we have 35 minutes times 60 seconds per minute and divide that by 4.187. Now, and so if we multiply out the 35 times 60, we have 2100 seconds. And so it's very important for us to get that right because if not, of course, we'll get the incorrect answer. And so the heat produced comes out to be 2200 multiplied by 2100 divided by 4.187. And that is and I kept 4 significant digits, 1.103 times 10 to the 6 calories. And so we can call that, you know, we can call that 1100. And let me do that again. We can call that 1.106 is fine, right? 1103 kilocalories might be, you know, a better way to do it. And it's not that it matters, but, you know, kilocalories is the most common way that this is written. 1.103 megacalories is good too, right? 1.103 megacalories. And so either one of that is fine for the way that you should really do this. Now the 1103, not really engineering notation, is it? Because the number is not supposed to go over 999.9999. But you know, some things that are not really engineering notation is acceptable in electrotech, and certainly kilocalories is one of them. Okay, so now we know that the heat produced is greater than Q. And so it's important to remember that when you're using the efficiency formula, because it's easy to make a mistake in that efficiency formula. And so the efficiency has Q divided by the heat produced and multiplied by 100%. Now I usually leave out the 100% for these calculations because we want efficiency as a decimal, right? And so Q then is going to be equal to the efficiency multiplied by the heat produced. And so our efficiency is 60%. So as a decimal, 0.6. And we're going to multiply that by our 1.103 megacalories, or I'll write it as 1103 kilocalories. And so now we find that Q is equal to, and right here I rounded it to 3 significant digits. So we got 662 kilocalories. Okay, so now the mass is relatively easy to find, right? Because we have Q equals MC times delta T. And delta T is 200 to 220. So we have 220 degrees. Oh, wait, no. Yeah, let me fix that. I'm getting a bit ahead of myself there, I think. Okay, so go back to 220 degrees, subtract 20 degrees, or, of course, 200 degrees is delta T. Okay, so then the mass, I think a capital M I should have used there, right? Q, no, wait, no. I fooled up a bit here because it's not the mass we're looking for at all, is it? It's the, it's C we're looking for, the specific heat of the material. And so, oh, here we go. Now, so C is equal to Q divided by the mass multiplied by delta T. And so 662,000, if you would, 662 times 10 to the 3 calories. Remember that everything is base units here. So Grams means 15,000 if there's a K there, right? And so that's an important one to remember. 15 times 10 to the 3 grams for kilograms, multiplied by 200 degrees C for delta T. And if you work all that out, you should come up with 0.2207. And so, you know, compare that to water at 1, that seems to be very dense. It's an aluminum alloy, and so that's what the calculation suggests for C. Now, the last part of that question, we were asked then to find the cost if the energy is 8 cents a kilowatt hour. And so for part C now, the cost is equal to the energy we already got the energy more or less in calories, right? But now, of course, that energy needs to be in kilowatts, multiplied by the, oh, that's kind of small there, the price per kilowatt hour, that should say. So now remember that our energy must be in kilowatt hours, and our cost per energy is, you know, 8 cents per kilowatt hour, or $0.08 per kilowatt hour, whatever is suitable. And so here you're going to see that the cost is low, so cents per kilowatt hour is what we would consider suitable. And so remember now, our energy was 2.2 kilowatts. And we want to multiply that by the time. And this time, we got to convert that to hours. So now, it's I'm putting down 0 point, but I haven't done the calculation yet, right? And so let's go back to saying that that was 35 minutes divided by 60, or times 1/60, right? Minutes per hour, to leave us with a time of hours. And now we want to multiply that by our 8 cents per kWh. And if you follow through the units now, of course, the kilowatts cancels with the kilowatts, and we're left with hours there, and that cancels with hours, and our unit is pennies or cents. And so the 35 divided by 60 is giving us 0.583 repeating in hours. So if you did that calculation first, you got that in your calculator there, the 0.583 repeating, multiply that by 2.2 and then multiply by 8, and you come up with, if you round that, 10.3 cents, which don't sound like very much, do it? And so remember that you only did that once, and it only took you 35 minutes to do it, right? And so I think that's probably appropriate at 8 cents a kilowatt hour. Now, if you're doing that continuously, or you're doing that over and over and over and over, of course, the price goes up.